Hello everyone. Here we have the concept of finite automata or finite state machine. We all know what is automata. Anything which is self-driving or self-acting is called an automata. What is finite automata? Finite here it means it has finite number of memory element. Finite number of memory elements. So therefore it is called finite automata, also called finite state machine. Memory element is nothing else but would be called states. Now we'll be discussing what is deterministic finite automata, what is non-deterministic finite automata, and non-deterministic finite automata with null transitions. First of all, starting with the deterministic finite automata. Deterministic finite automata is defined as 5 by 5 tuple. 5 tuple Q, sigma, Q naught, A and delta. What is Q? This capital Q is finite set of states. Finite set of states, like every machine will have some finite set of states or memory elements. Sigma, finite set of alphabets or symbols. We already know this definition. Q naught is the initial state of the machine. Every machine or every automata will have an initial state. Initial state, there is exactly one initial state in each machine. So therefore Q naught belongs to Q. There is Q naught, this initial state will belong from the main set of states. A is the final set of states or accepting state. Remember that A is subset of Q. It means that we can have more than one state as the final state. Then we have this transition function. Transition function is defined as Q cross sigma to Q. I'll explain this. What is Q cross sigma to Q? If we have some automata with Q, that is, we suppose there are two states, Q naught and Q1. Sigma, two symbols are given, suppose A and B. So what will be the elements of Q cross sigma? It will be Q naught A, Q naught B, Q1 A and Q1 B. So this Q cross sigma to Q, the function would be like this. Q naught A, Q naught B, Q1 A, Q1 B to Q. So therefore the Q are the elements of Q, Q naught and Q1. So what we are trying to explain, the transition function in deterministic finite automata requires that we need to show the transition from every state. Suppose Q naught is the state. For Q naught we need to show the transition for A as well as B. For Q1 we have to show the transition for A as well as B, and that too exactly once. Exactly one transition by reading an input. Suppose we are at state Q naught. For deterministic finite automata, we need to show on reading A the transition of Q naught as well as reading B the transition of Q naught. Similarly, for Q1 also we need to show the transition for the symbol A as well as B. Then only we'll call this machine as the deterministic finite automata. If there is some machine where we have a state Q naught and you are just giving the transition A and the transition B is not visible and sigma has B also. So in that case we'll say that this machine is not deterministic. So for deterministic finite automata, just remember this transition function. Definition says that Q cross sigma to Q, it requires that for every state we need to show the transition for each symbol in the sigma, and that too each transition has to be exactly once. then only it will be a deterministic finite automata. That is, for example, in this case, Q naught on reading A, we assume that it is going on Q naught. Q naught on reading B, it is going on, say, Q1. Similarly, Q1 on reading A, we assume that it is going on Q naught, and Q1 on reading B, it's going on Q1. So this will be a deterministic finite automata. But suppose, take the example of this kind. Suppose if this is Q naught on reading A is going on state Q naught, also going on state Q1, this will not be a deterministic finite automata. It should be having exactly one transition. Q naught on reading A should go to exactly one state. Q naught on reading B should go to exactly one state. As well as each transition has to be visible. Q naught on reading A as well as Q naught on reading B. Q1 with A and Q1 with B. Then only this is deterministic. So now we'll be seeing some of the examples how to design the machine. First of all, we need to understand the language. Remember that one more thing you need to remember, finite automata accepts regular languages. Any finite automata, be it deterministic, non-deterministic, or non-deterministic with a null transition, all of these are going to accept the regular languages. Now we'll see the first example. Design deterministic finite automata for the following languages. Let the languages R over sigma. Remember that we need to have this value. Sigma is 0 and 1. And let the language is 0 raised to the power n for any n greater than equal to 0. Hope you all are able to write the regular expression for this. It is like 0 raised to the power n, where n is greater than equal to 0. So we will have a string. Language has kind of string. It has null. 0 raised to the power 0 will give you a null. It is 0 raised to the power 1, 0 raised to the power 2, 0 raised to the power 3, and so on. Such type of strings are there in this language. Regular expression for such language is 0 star. We all know that. And we need to create deterministic finite automata for this language. Now, first of all, we need to have the states. We will represent states with a circle. Draw a circle. This is the initial state. Initial state will have this arrow sign on it. So this is the initial state. We'll see what is accepted, what things are accepted, what strings are accepted by this machine. Null is accepted. Remember, when null is accepted, so we'll make initial state as the final state. Final state or an accepting state, will represent this with double circle. This is the final state or accepting state. For initial state, we will have this symbol circle with this arrow sign. This is the initial state. Remember, whenever you have a language in front of you, see if the language is accepting a null string. If it is accepting a null string, it means that initial state is the final state. For this example, we have a null string in the language, so therefore initial state is the final state. And then we'll see what else we can do. That is, it is accepting any number of zeros. Any number of zeros are accepted by this language, so we'll put a 0 here. Any number of zeros are accepted. Now, is this a finite automata? It is a finite automata, but it is not deterministic one. We need to represent, if this is Q naught, we need to represent what will happen when Q naught reads 1. So we need to show the transition for sigma. Elements in the sigma, all the elements in sigma, that is 1. Yeah, there are two symbols in the sigma, 0 and 1. So we took 0 here for this transition. 0 is there. So we need to show the transition of 1 on the state Q0. Q0 on reading 1 is going to some another state, say Q1. Now for Q1, if suppose we have a 1 encountered in this language, it should not be there in this, it is not belonging in the language. So whenever 1 is encountered, it will go to some another state, and this state will, for any 0 or 1, it will stay in the same state. So such type of states are called a trap state, because once we reach Q1, will remain there forever, either 0 or 1. The machine is not going to move from anywhere from Q1. It is going to stay on Q1 forever, either reading 0 or 1. It means that such states will call it trap state. So now this is a deterministic finite automata. We can clearly see there are two states, Q0 and Q1. For each states, we have the constraints are satisfied. That is, we have to show the transition for each symbol in the sigma, for 0 and 1 both, and that too exactly once. For 0, there is exactly one transition. Q0 on reading 0 is going on Q0. Q0 on reading 1 is going on Q1. All string of this type, that is 0 raised to the power n greater than equal to 0, are accepted by this language. We can clearly see the initial state is also the final state. Single 0 is accepted, two zeros are accepted, n zeros are accepted, but once the machine sees a 1, it will move to the trap state, and once we reach the trap state, it will be there forever. So this is one example. We'll see more such examples. Hopefully clear to all of you. Please let me know in the comment box that you all are clear with the concept of this particular example. We'll see more of the examples. Now the next question, that is 0 raised to the power n for n is greater than equal to 0. Try to understand the language. What type of strings are there in this language? 0 raised to the power n greater than equal to 0, it means null is accepted. The second 0, 1 raised to the power 1. 0, 1 raised to the power 2, which is equal to 0, 1, 0, 1. Similarly, 0, 1 raised to the power 3, 0, 1 raised to the power 4, and so on. So the regular expression for such type of language, we all know it has to be like this. Now, since we already have seen that whenever we have a null string in the language, what we need to do, make initial state as the final state. Initial state is also the final state, as the null string is also accepted. Now, once it accepts a 0, single 0, it will move to the state Q1, and once Q1 accepts 1, go back to Q0. So we can see that 0, 1, 0, 1, Q0 to Q1, 0, and then back to Q0 by reading 1. So we are reading 0, 1 any number of time, and since the initial state is the final state, null is also accepted. So 0, 1 is accepted for any n greater than equal to 0. So the requirement for acceptance of 0, 1 raised to the power n is complete. But is the machine completed yet? No, it is not deterministic finite automata as of now, because for Q0 we cannot see the transition for symbol 1, and for Q1 we haven't given the transition for the symbol 0. So for if Q0 reads some 1, it should go to some another state, say Q2. And since we can clearly see the string, if it starts with a 1, it is not in the language, so it should go to the state which is a trap state. Similarly, for Q1, we have shown the transition for 1, but it doesn't have transition for 0. So we'll put again, if we have a 0, Q0 to Q1 is 0, and then again at state Q1, if the machine sees symbol 0, it means we will have a double zero in between, which is not there in the language. We must have a string, all the strings of this form 0, 1, 0, 1, 0, 1, such type of string. There are no consecutive zeros in any of the string in the language. So therefore, if Q1 sees a 0, it will go to the state Q2. So therefore, we are done with this deterministic finite automata. See, check all the constraints. What is the constraint requirement here? Q0 has to show the transition for both the symbol. What are the sigma? Sigma has 0 and 1. So for Q0, we can see that there is a transition for symbol 0 as well as 1. For Q0 also we have a transition for 0 as well as 1. For Q2 also we have a transition for both the symbols 0 and 1. So therefore, this is the deterministic finite automata for the given language. Now the next question says that strings always end with 1. Like we have any combination of 0 and 1, but the string is always ending with 1. This is the language for uh, uh, this particular example. The regular expression for this language is 0 plus 1 star, whole star followed by a 1. So whenever we have such type of example, check if the language has a 0 null string. It doesn't have a null string in it. So we'll not make first state, initial state as the final state. Here, Q0 is not the final state. What is the requirement? It says that string must have all strings in the language must end with a 1. Suppose I take 1 here and we reach Q1 on reading 1, and so therefore it should be I'll make it a final state. Whenever we have zeros, any number of zeros before 1 stay on Q0. Q0 on reading 1 is in the state Q1. After 1, we can have any number of ones as it is ending with a 1. But what will happen if it reads a 0? If Q1 reads a 0, go back to state Q0. So this is the example for deterministic finite automata for the given language. Whenever the string is ending with 1, we can clearly see, assume any string which ends with 1, you will see that this machine is going to accept it. For example, if I have any string 0, 1, 0, 1. So this is the string that ends with a 1. We can see that we will move start from Q0. Q0 on reading 0 stays on Q0. Q0 on reading 1 is going to the state Q1. Q1 on reading 1 is going to state Q1 only. Q1 on reading 0 is going on Q0, and Q0 on reading 1 stops on state Q1, which is an accepting state. So machine stops. Whenever the machine stops by reading all the input symbols on, and it stops on uh, any of the accepting state, then we say that the string is accepted by the machine. Now assume that we have some string, input string of this form 0, 1, 1, 0. So start again. Q0 on reading 0, it goes on Q0. Q0 on reading 1, it goes on Q1. Q1 on reading 1, it goes on Q1. Q1 on reading 0, it goes on Q0. We have consumed all the input symbols and the machine has stopped. It has stopped on which state? It stops on Q0. Q0 is not the final state. So therefore we say that this string is not accepted by the machine. So based on the automata we have designed, it is always accepting the strings that ends with a 1. Now the next question says that string starts with 0. Starts with 0. So again, what is the regular expression for this? Starts with a 0. It can be followed by any number of 0 or 1. We'll start with Q0. It is not accepting a null string, so I will not make initial state as the final state. Make sure we read a 0. we reach state Q1. Once the machine has seen Q1, the requirement is fulfilled. So we'll say that it is accepted. And after this, we can have any number of 0 and 1. Any number of 0 and 1 on Q1. On Q0, if suppose machine sees a 1, and it should not start with a 1, so it should go to state, say Q2, which is the trap state. And once the machine reach there, it should be like in the trap state, it will be there forever. So therefore this is the deterministic automata for the given language. We'll be having more questions, more examples on deterministic finite automata in the next video. Thank you for watching, and hopefully your concepts are clear so far. Let me know in the comment box if you have some query related to the concepts we have discussed. And if you have some new questions, please put in the comment. Thank you so much.